if you can, we will start. Welcome everybody to the season 7 of the online seminar series Machine Learning Needs Mathematical Optimization. So we will be running this season until May, and we are extremely happy to see many of you in this session today. So welcome everybody. So now is the time to introduce our speaker, Shiqian Ma, who is an associate professor in the Department of Computational Applied Mathematics and Operations Research at Rice University. His current research interests include theory and algorithms for large-scale optimization and application in statistics, machine learning, and signal processing. He has published in very prestigious journals in the field such as Mathematical Programming, SciAm, Journal on Optimization, but also in proceeding from leading conferences in machine learning. And his research is supported by, among others, the NSF, and he has received also several awards across his career. I can mention the Informs Optimization Society, the Journal of the Operations Research Society of China, and SciAm Review. Shiqian is also an associate editor of the Journal of Machine Learning Research, the Journal of Optimization Theory and Applications, and he's an area chair in ICML, NeEDS, and other leading conferences in machine learning. And as you may have heard, he's extremely busy because he's also leading this year the Informs Optimization Society conference, which he has told us that is very, very popular this year with more than 400 talks. So we thank you for coming today, although you are very busy. For the audience, please remember that Shiqian is happy to take some questions on the go if they are very urgent, and otherwise we will leave the time for questions at the very end. So thank you for coming today again, and yeah, we are looking forward to hearing about your research.
Okay, thank you, Dolores. Thank you very much for the very nice introduction. I also want to thank the organizers, so Dolores and Emilio, for inviting me to give a talk in this seminar series. I think it's a great honor to speak in this seminar. Okay, so today I will talk about the decentralized bilevel optimization. So bilevel optimization has been a very popular research area in the recent years. So today, basically, I want to give a survey about the recent progress in this direction, especially the algorithms and applications of bilevel optimization in the decentralized network setting. Okay, so the bilevel optimization problem can be formulated like this. So I hope you can see the line I draw here. Basically, in the bilevel optimization problem, we have two levels. In the upper level, we want to minimize a objective function. That's the same as the Euler optimization problem. In the lower level, we actually want to minimize another optimization problem. So basically, in the lower level problem, the optimal set of this optimization problem gives a constraint to the upper level problem, right? So this is the basic formulation of bilevel optimization. We have a upper level problem, we have a lower level problem, and you notice that we have two different functions, right? F and G. Usually we assume that F and G are both smooth, so we can compute their gradients. And also, usually we assume that the lower level problem the lower level function G is strongly convex with respect to the variable Y. Okay. If that's the case, then for the lower level problem, this inclusion here can be changed to a equation, right? Because for any fixed x, the optimal solution y star of x is unique, right? Okay, so if this function g is equal to the negative f, then this whole problem actually reduces to a minimax problem. This is a minimax problem. So then basically you can see that in minimax problem, there are two decision makers, right? One want to decide x, the other one want to decide y. And these two decision makers, they have the same objective function. It's just one of them wants to minimize it, and the other one wants to maximize it, right? However, in the bilevel optimization problem, these two decision makers, they have two different criteria. They have two different objectives, right? They have two different functions to minimize, right? Okay, so this is a brief history about bilevel optimization. The first time that bilevel optimization appears in the literature, actually in the economics literature, was due to Stackelberger. In his book published in 1952, he actually modeled economics problem as a two-player game. But these two players, they have different objective functions. And this problem can be formulated as a bilevel optimization problem. And he called the upper level decision maker as a leader and the lower level decision maker as a follower, right? So these two, these two decision makers, they make their own decisions, but also these two decisions will affect each other's decision. So they want to make the decision, cooperatively so that they achieve their own respective goals. Right? Later in 1973, so this paper by Bracken and McGill, this is the first time that bilevel optimization problem appears in optimization literature. And in this paper, they formulated a resource allocation problem arising from a military application as a bilevel optimization problem. The research since then has been quite sparse. I think one of the main reasons is that this kind of bilevel optimization problem, due to its structure, is very challenging to solve. So people didn't find very efficient algorithms for dealing with this kind of problems. Recently, bilevel optimization problem became a very active research area due to some emerging applications. So in the next few slides, I will talk about some applications of a bilevel optimization problem, especially in the machine learning field. The first application is called hyperparameter tuning or hyperparameter selection or hyperparameter optimization. So basically, excuse me. So for example, let's look at the first application here. This is the lasso problem, right? In the lasso problem, we want to minimize, first of all, we want to minimize a loss function, right? So this is a least squares loss function. And we want this vector beta to be sparse. So we want to minimize its L1 norm, right? This in front of this L1 norm, there is a parameter mu. And this mu is, for example, a penalty parameter, which can balance the two terms in the objective function, right? So this mu is a hyperparameter, okay? So usually we need to give this mu beforehand, and then we design an optimization algorithm to solve this particular problem for a fixed mu, right? But the question is, what is the best choice for this mu, right? So that means we want to tune or we want to select a good hyperparameter mu. So this kind of problem is called hyperparameter tuning or hyperparameter selection. Right. So another example in the support vector machine problem, we also have a hyperparameter mu, right? And nowadays in deep learning, right, we use a deep neural network to train machine learning models. And when you design this neural network, then of course you need to decide the neural network architecture, right? So how many layers, and every layer, how many neurons, and so on. So those parameters, they're all hyperparameters, right? In practice, people need to tune them, and that can be very time consuming. For example, one classical way to choose the hyperparameter is by the following so-called cross-validation procedure. For example, we partition the, let me use a pen here. So for example, we partition the index set, right? So this is the number of data we have. We partition this set into k different parts. And for the data set, we also partition the data using the corresponding partition. So then we have k parts of the data, okay? And every part can be used as a training data, and the other parts, so the rest of the data can be used as the validation data, okay? So then the classical procedure to determine this hyperparameter mu is to do a grid search. So for example, we do this, we do the following procedure. For given hyperparameter mu, we use part of the data set as a training data and the rest of data as a validation data. So we use the training data to optimize the loss function, okay, to decide the model parameter. And then using the model parameter, we can use the validation data to calculate a validation error, right? And then for the k data sets, we take the average of the validation error, and we see whether this error is small or not, right? So then we just repeat this procedure for many values of mu. And in the end, we choose the one making the average validation error the smallest one. Okay, so basically you can see that this procedure is quite time consuming because every time we need to solve k different machine learning models, right? For example, if we're doing SVM, then we need to solve k different SVM models. And also here we need to repeat this procedure for many values of mu. And that means you can only test a finite number of choices of mu. And whether they cover the best choice or not, we don't know, right? Okay, so it turns out that this hyperparameter tuning problem can be formulated as a bilevel optimization problem. In this bilevel optimization problem, so here this is the bilevel optimization model. In the upper level, we want to choose the hyperparameter mu, and also the model parameters beta 1 up to beta k, because we have k models. In the lower level, basically we solve these k different machine learning models for the fixed mu. Okay, overall, basically we are minimizing the validation loss function in the upper level, and in the lower level we're minimizing the training loss. Okay. Basically, we want to choose the best mu such that those model parameters, right, given by the lower level problem will also minimize the validation error in the upper level. In this way, we expect that we can find the best choice of the hyperparameter mu. Right. So this is the bilevel optimization problem for this particular hyperparameter tuning application. The second application is called meta learning. In meta learning, for example, we have m different learning tasks. Okay, and each learning task is associated with a data set. And in this data set, there are two parts. One part is the training data. The other part is the testing data. Right. In the meta learning problem, what do you want to do? The goal of the task, for example, TI, is to learn the task-specific parameters WI and a shared hyperparameter lambda. Okay, using the training data to minimize the loss function over the tested data. Okay. So now let me give you some explanations here. So what is a shared hyperparameter lambda here? For example, this shared hyperparameter lambda can be the step size or the learning rate of the algorithm that we used here. So for example, let's see if I want to use SGD, right, to solve this class of machine learning tasks, right? And I don't know how to choose the step size, right? And then one way is, for the different tasks, I just tune a different step size. but of course that's not ideal. That's very time consuming. The goal here is that I want to choose a step size or the learning rate such that this algorithm will work for a lot of similar tasks. Okay, so then how do I do that? Then this hyperparameter lambda, which is the step size or the learning rate of the SGD algorithm, right? This one can be trained using those different machine learning tasks, and this problem can be formulated as a bilevel optimization problem, right? So, for example, in this bilevel optimization problem, the lower level, I just solve these different machine learning models with a fixed lambda. And then in the upper level, I try to minimize this lambda such that those validation error is minimized. Right. So this is another application. This is called the meta learning. The next application is called data hypercleaning. The goal here is to train a linear classifier for some classification, for example, the MNIST dataset. Right. However, the situation here is half of the training labels are corrupted, right? So the data labels, right, they're not correct. So then how to clean the data, right? How do we know which data point is corrupted? And this problem is called the data hypercleaning, and this problem can be solved using a bilevel optimization approach. For example, in the upper level problem, we use a cross entropy loss function, okay, on a cleanly labeled validation set. So for the upper level objective function, it is corresponding to the cleanly labeled validation data set, right? For the lower level problem, we have a weighted cross entropy training loss plus some regularization. Okay, so here this is the log function, this is the loss function. Okay, this one is the regularization, and this sigma of lambda I, actually this one gives the weighting for those data points, right? So basically, if the sigma lambda I is small, then that means this data point, xi, yi is corrupted, because in the training model, we don't pay much attention to those data points, right? So this is the lower level problem. The upper level function is similar to this function g, but probably without this regularization term, right? So then again, right, you can see that in this problem, by formulating this problem as a bilevel optimization problem, we're able to decide the weighting parameter lambda I. Then we're able to know which data might be corrupted data. Okay, so these are some applications of a bilevel optimization problem. So now let me talk about the algorithms. A very natural idea to solve this bilevel optimization problem is to use gradient method, right? So so we're now looking at this upper level problem. So how about I just do a gradient descent step, right, for the upper level problem. Then here, of course, I need to compute the gradient of the upper level function. This gradient is the gradient of phi at xk. Because this gradient is not the same as the traditional gradients we're talking about. Usually in the bilevel optimization literature, this is called the hypergradient, right? So then the next question is, how do I compute the hypergradient? Right? Okay, so to compute the hypergradient, we can use a chain rule, right? So you can see that the upper level function, right, phi of x is equal to this one, right? And this function f has two components, right? X and y star of x. Here, when you compute the gradient with respect to x, then you need to also consider the function y star here, right? So when we use chain rule, then this gradient is equal to this. So first we take the partial gradient, right, for the first variable, and then we take the partial gradient for the second variable. But the second variable y star of x is a function of x. So then we also need to take the gradient of y star. So then the next question is how to compute the gradient of y star, like the red part. It turns out that when the lower level function g is strongly convex with respect to y, then we have actually a closed form solution to represent the gradient of y star. Okay. Basically, we look at the optimality condition of the lower level problem, right? Then because y star is the optimal solution, we know that the gradient with respect to the second variable is equal to 0. And then for this equation, we further take the derivative with respect to x, right, for both sides. Then we get the following equation. So 0 is equal to this one. And then that corresponding to, we further take the gradient for x, right, for these two components. And then it turns out that here, because we have y star of x, then we take the gradient again, we obtain the gradient of y star exactly. Okay, so we here we obtain an equation about the gradient of y star. And using this, we're able to give a closed form expression for computing this gradient of y star. Right. So a lot of bilevel optimization algorithms are based on this formula. Okay. All right. Then the gradient method for solving the bilevel optimization problem can be summarized in the following. So here we have two loops. In this part, okay, this part of the for loop, this one is to approximately solve the lower level problem when x is equal to xk. So basically, after t iterations here, we have a ykt. Ykt is a approximation to y star over xk. Right. And once we have the approximation to y star over xk, we can use the formula that we just derived, right, to estimate this hypergradient here. Right. So this is the estimation to the hypergradient, and this color part per gradient here. Right. So this is the estimation to the hypergradient, and this color part here, this is the approximation to the gradient of y star of x that we just developed in the previous slide. Right. And then once we have an estimation to the hypergradient, we just run the gradient descent step to update x, which is to solve the upper level problem. Okay, so this is a very natural idea about a gradient method for solving this bilevel optimization problem. Then basically, if you look at this algorithm, very easily we can find that there might be some issues, and we will ask some questions. The first question is how to avoid the loop in solving the lower level problem, right? As you can see, in this algorithm, we have two for loops, right? So this algorithm is basically of a double loop structure. This is not very nice, right? So in practice, sometimes we want to avoid the loop when we solve the lower level problem. So this is the first question. The second question is how to avoid inverting the matrix, right? As you can see in the brown color part, right? So when I want to compute the estimation to the gradient of y star, I need to invert a matrix, and that's not very ideal in practice, right? How do I avoid that? The next question is how do I avoid computing the Jacobian or the Hessian matrices? Right, they are the second order derivatives, right? So those second order derivatives, they appear here. This is the Jacobian of G. This is the Hessian of G, right? So how do we avoid computing those items, right? So answering each of the questions here actually leads to a whole lot of research works, right? So this is basically what people in bilevel optimization community are doing. Okay, they try to design different algorithms to address those issues. Okay, now let me talk about decentralized bilevel optimization. So decentralized bilevel optimization means that we want to deal with the bilevel optimization problem in a decentralized network. Okay, in the decentralized network, basically, all the nodes or all the agents, right? They can only communicate with their neighbors, right? In this problem, as you can see, now in the upper level problem, we're considering a summation as our loss function, right? We have number n here. N is the number of agents. Okay, and each agent has a data which correspond to the function fi here. In the lower level problem, we also have a function gi. So gi is also the data corresponding to the data for the ith agent, right? So each agent can only access their own data, which are fi and gi. All right. If they want to get the information from their neighbors, they need to do communication with the neighbors. Right. For the decentralized problem, usually we have this kind of data heterogeneity property, right? Because the data, right, stored on different devices, they might be different, right? So the distributions of this data, they can be very different. So this actually poses a lot of challenge when we solve this decentralized bilevel optimization problem. Okay, so a very natural idea to design a decentralized algorithm for solving this bilevel optimization problem is that in every iteration, each of the agents can compute their own estimation to the hypergradient, right? And then once they have the estimation to the hypergradient, they just communicate with their neighbors and also update their local copy of the descent variable x, right? So here I have a wij here. Wij is actually the component of this the matrix W, which characterize the property of the decentralized network, right? So then this step is actually a gradient descent step, right? However, it turns out that computing the local hypergradient is much harder than the single agent case. Okay, now let's look at the local hypergradient, right? The local hypergradient means that I want to compute the gradient for the phi I. Phi I is equal to fi of x and y star of x, right? So again, we use a chain rule. Then we found that here we need to compute the gradient of y star, and using the discussions we talked about earlier, we know that this is equal to this one. Right? However, now we need to notice that this function g is equal to the summation of this function gi, right, across the different agents, right? Then that means this blue part, right, when we compute the the gradients of y star, we actually need to know the global information of the function g, right? For each agent I, right, this agent I does not have the access to the global information, right? So if we want to compute this, then we need to compute this quantity in the decentralized network setting through communication, right? So this issue was actually addressed in our recent work. We actually proposed a decentralized algorithm to compute this hypergradient estimation, and this is the first decentralized algorithm for solving the bilevel optimization problem. Okay, so our idea is actually quite simple, right? So let me go back to the previous slide. So if we want to compute this, this quantity, right? This is the global information, the gradient of y star. Apparently, this is equal to solving a linear system, right? And solving a linear system is actually equivalent to minimizing a quadratic function. So we just formulate this problem as minimizing a quadratic function, and this problem is strongly convex, right? And then we ask all the agents to cooperatively solve this quadratic programming problem, and then after converging, then each agent will get an estimation to this variable z. By the way, we use this z to denote the the quantity that we are looking for. That's the gradient of y star. Okay, and after each agent has an estimation to the hypergradient, right? Then they have an estimate to this variable z. Then they just use their local copy of the zi to compute their local hypergradient. Okay, so this is one way to address this issue. Of course, you can see that, right? So this procedure is still very complicated because to compute every hypergradient, you need to run an iterative algorithm, right? In this decentralized network, right? So this is the full description of our decentralized bilevel optimization algorithm. So first of all the agents, right, they start with some initial points, and then in step 1, all the agents, they cooperatively solve the lower level problem, right? To solve the lower level problem, then basically we run the gradient descent for the variable y. Here we just adopt some classical technique from the decentralized optimization literature. For example, here this gradient is denoted by VIK, and the VIK here is updated in this way. This red part is the so-called gradient tracking technique, and this was used a lot in the decentralized optimization literature, and people already demonstrated that this technique can help speed up the convergence of the algorithm, right? Okay, so step 1, all the agents, they cooperatively solve the lower level problem. And once we solve the lower level problem, and then we run the decentralized algorithm that we talked about earlier to solve this strongly convex quadratic optimization problem to estimate the local hypergradient, right? So the local hypergradient is denoted by this one. And then all the agents, they will update their own copy of the variable x. Right. To update the x, we run another gradient descent step, of course, in the decentralized optimization setting. Right. So again, the gradient here is denoted by UIK, and when we update the UIK, we again use this gradient tracking technique. Okay. So this is what we do in the case iteration. All right. And in the end, after capital K of iterations, we stop the algorithm, we output the average of these local copies as the final output. Right? So this is our decentralized bilevel optimization algorithm. Okay, and we can also do the the decentralized stochastic bilevel optimization problem, because we know that in the machine learning, deep learning applications, right, usually the the objective function, right, or the loss function, they're of this kind of form. They're expectation of another function, or sometimes you have the discrete data sets. Then this loss function can be written as a finite sum, right? In this case, because we cannot access all the data sets, or maybe we don't know the distribution, right? So we can only access the stochastic gradient instead of the exact gradient. We can correspondingly design a similar algorithm, basically just replace all the gradient estimation in the previous slide by stochastic gradient. Okay, so we have two results here. Basically, we have two algorithms. One is for the deterministic decentralized bilevel optimization problem. The other one is for the decentralized stochastic bilevel optimization problem. In both cases, we can show iteration complexity results for our algorithm. For the deterministic algorithm, we can show that the minimum of the norm of the hypergradient squared is in the order of 1 over k. For the stochastic version, we can show that the expectation of the norm of the hypergradient squared is in the order of 1 over square root of k. Okay, so these are some theoretical results about the algorithms. And we have another paper published in SML last year. In this paper, we actually improved the sample complexity of the previous algorithm, the decentralized stochastic optimization algorithm. We improved the sample complexity using two techniques. The first technique is that when we compute the Hessian and the Jacobian, right, we notice that we don't know we don't need the Hessian or Jacobian matrices. We only need their product with the vectors. So we propose to compute these matrix vector products directly without explicitly computing the matrices. This will improve the sample complexity. Another improvement is for the upper level problem. we incorporate a moving average technique. So this is very similar to the the momentum technique or the Nesterov's acceleration technique, right? Used in accelerated first order method. Basically, when the agents update those variables x, right? They use the gradient denoted by RIK, and this RIK is updated in this way. So this HIK denotes the RIK is updated in this way. So this HIK denotes the local hypergradient estimation. Okay, so this the second line here, this is called the moving average. So we use a moving average to update the gradient, the hypergradient. So combining these two techniques, we were able to improve the sample complexity of the algorithm from epsilon to the -3 to the order of epsilon to the -2. Right? So I'll skip the details because I have more materials that I want to discuss. The next topic is about single loop decentralized bilevel optimization algorithm. So this is the algorithm that we showed before, right? This is a very natural idea about the gradient descent method, right, for solving this bilevel optimization problem. And here we propose some possible improvements over this algorithm. So for example, we set this capital T here equal to 1. That means in this for loop here, actually we remove the loop, right? So the whole algorithm becomes a single loop algorithm. The second improvement is for this red part, right? So here we need to solve a linear system. So again, we notice that solving this linear system is equivalent to minimizing a quadratic function, right? However, we don't want to run another iterative algorithm to minimize this quadratic function, right? So here we propose to just run one step of gradient descent to approximately solve this quadratic programming problem, right? Okay, so this idea is actually not new. This idea was actually originally proposed by Del Rio et al. in this paper, NeEDS paper published in 2022. In this paper, they actually proposed an algorithm which is called SOBA. In the SOBA algorithm, this is their update. So they maintain 3 iterative sequences, right? They have YK, VK, and XK, right? So YK, of course, YK is the descent variable, right, for the lower level problem. XK is a descent variable for the upper level problem, and VK is the variable in the in that quadratic optimization problem when we want to compute the hypergradient, right? It turns out that they propose this algorithm. By the way, this is a single loop, right? And they can show the convergence. So in our work, we want to extend this SOBA algorithm to the decentralized bilevel optimization setting. Okay, one challenge here is the existing decentralized bilevel algorithms. They all need to make some assumption, which is called the heterogeneity assumption, right? For example, the moving average decentralized stochastic bilevel optimization algorithm that we just talked about in our SML paper last year, we actually need to assume the following. Okay, so this assumption actually indicates that all the gradients for the lower level problem, they're not far away from each other. Okay, there exists a delta such that this difference can be uniformly bounded for any x and y. Right? So this is actually a very strong assumption. Unfortunately, most of the decentralized bilevel optimization papers, they need to assume something like this. Okay. In our work, we want to design a decentralized bilevel algorithm without using any heterogeneity assumptions. And without this heterogeneity assumption, the main difficulty is to bound the sequence YK and VK. Okay. Some papers, they just assume that this is true without justification. Okay. Our novelty in our paper is that we achieve this by using a very novel projection procedure. We project these two sequences onto a Euclidean ball. So now let me give you this is the full description of our algorithm. In the case iteration, we do this. Okay. So here we update yk, here we update vk and xk. Right. So these are 3 steps. They're all gradient descent steps in the decentralized network. So the red part here, I have a projection here. I have another projection here. This ry and rv, they denote the radius of the Euclidean balls that I want to project the iterate onto. Right. So these 2 parameters, ry and rv, they are pre-given. Right. They are predetermined. So we know how to choose them. And these these variables dy, dv, dx, they are the gradients. It's just when we update yi, vi, and xi, we don't use those gradients directly. We again do something similar to the gradient tracking technique. This is a standard practice in the decentralized optimization literature. So I want to emphasize again that our algorithm is a single loop, and there's no matrix inversion. Okay, and the the parameters ry, rv, they're predefined. We know how to compute them. The boundedness of this sequence xk can be proved in our algorithm. So this is our convergence results. We can actually show that the norm of the hypergradient squared, this quantity is at the order of 1 over square root of k. K is the iteration number. All right. So I want to emphasize again that we do not need any heterogeneity assumption. In my opinion, this is a very significant improvement over existing methods for decentralized stochastic bilevel optimization. Right. However, you may notice that in this algorithm, we still need to compute the 2nd order derivative, right? The Jacobian and the Hessian matrices. So in the next few minutes, I want to talk about a fully 1st order algorithm for solving bilevel optimization problem. Okay, so this algorithm will be based on the so-called value function based reformulation. I think this is a very interesting subject. So this is the original formulation of the bilevel optimization problem, and we can reformulate this problem as this. Okay, so then you can see that basically I do not have the lower level optimization problem anymore, right? This lower level optimization problem is replaced by this nonlinear inequality constraint. So here I define a new function g star. The g star of x is the optimal function value of the lower level function g when x is given. Okay, so it can be proved that it's very simple to show that these 2 problems, they're equivalent. Now the latter problem here is actually a single level constrained nonlinear programming problem, right? We no longer have a bilevel structure. Right? This is reduced to a classical constrained nonlinear programming problem. So many tools from a nonlinear programming problem can be used here. All right. So here I want to talk about work by Kwong et al. They proposed this fully 1st order stochastic algorithm for solving this bilevel optimization problem. Their algorithm is based on this reformulation. They write down the Lagrangian function for this problem, and the k result here is that they can prove when lambda is large. By the way, the lambda is the Lagrange multiplier for this inequality constraint, right? So there's only one constraint, right? So lambda is a scalar. They can prove that when lambda is large, the following inequality holds. So basically, they can show that the hypergradient, right, the gradient of phi is very close to the gradient of L lambda star. So what's L lambda star? L lambda star of x is a function defined in this way. So you minimize the Lagrangian function with respect to y. Okay, you obtain the L lambda star, right? And then that means for a fixed large lambda, we can use the gradient of L lambda star to approximate the hypergradient here. And it turns out that you can compute this gradient of L lambda star relatively easier. Okay, so this is their algorithm. Basically, here they have two loops. In the inner loop here, they update a sequence zk and also a sequence yk, and they use zk to approximate this y star of xk, and they use yk to approximate this y lambda star of xk. So due to the time constraint, I think I will skip some of the details here. Once we know the the zk and yk, then we're able to compute this red part here. This is actually the approximation to the gradient of L lambda star of xk. And we know that when lambda is large, right, we can use this one to approximate the hypergradient. And then also in every iteration, they increase this estimation of the Lagrange multiplier lambda k. Okay, because we want lambda k, want lambda to be large, right? So then you can see that this is a fully first order algorithm, right? You don't need to compute any second order derivatives. And we have a recent work. We actually extended this fully first order method to a federated bilevel optimization problem, right? So that's also a fully first order method. Okay, so we also have a recent work talking about Riemannian bilevel optimization. So what is the Riemannian bilevel optimization? Riemannian bilevel optimization problem is this one. Basically, in Riemannian bilevel optimization problem is this one. Basically, in both the upper level problem and also the lower level problem, we have two constraints. The upper level problem, we have constraint x in M, and a lower level problem, we have y in n. These two sets, M and N, they are both Riemannian manifolds, and also they're also non-convex constraint sets. Okay, so apparently this is something more challenging. We have a recent work actually addressed how to design algorithms for solving this kind of Riemannian bilevel optimization problem. And also we noticed that there is a concurrent work by Han et al. They actually talk about the same topic. Okay, so now I think it's time for me to wrap up. To give a summary, in this talk, we talk about the recent advances on algorithms about the bilevel optimization problem. So when the lower level problem is strongly convex with the variable y, we know that we can run the gradient or the hypergradient method to solve this problem. Then a very crucial issue is how to compute the hypergradient, right? And from that, we designed the gradient descent algorithm. Then there arises three very important research questions. The first question says how to avoid the loop in solving the lower level problem. The second question is how to avoid inverting the matrix when we compute the hypergradient. The third one is how to avoid computing the second order derivatives when we compute the hypergradient, right? So answering each of the questions here will lead to a lot of research works, right? We also talk about the decentralized bilevel optimization problem. We discussed the difficulty here, right? The main challenge is that when we compute the hypergradient in the decentralized network, then every node actually needed the global information of the lower level function to estimate the hypergradient. And we designed a decentralized algorithm to address this issue. And recently we have a new work. We designed a single loop decentralized bilevel optimization algorithm. This algorithm is a single loop, and there's no matrix inversion. And very importantly, we do not need any heterogeneity assumptions. Right. In the end, we also talk about the fully first order bilevel optimization algorithm. We first discussed the algorithm designed by Kwong et al. We also talk about briefly mention that we recently extended this algorithm to a federated bilevel optimization setting. And we also have a recent work talking about Riemannian bilevel optimization. So with that, I think I will stop here. So this is a list of bilevel optimization papers from my research group. Thank you very much for your attention. So now I'm open for any questions.
Thank you very much, Shiqian, for such a great presentation. For the audience, if you would like to ask questions, please raise your hand and we will give you rights to the camera and the microphone. It was really good to see, Shiqian, the applications that you had at the very beginning for the different.
Yes, thank you. Yeah, I think this is a fascinating research area. I do see that. Yeah, this area has a lot of potentials and has many interesting applications.
Yeah, certainly. I do agree. There don't seem to be questions from the audience, so I think we are going to leave it here, Shiqian. And in any case, you may have more questions offline, as we will put this the recording of this video in our YouTube channel. So thank you so much for bringing us very, very, very recent work that you have done with your team. And to the audience, please remember that we will be back next week, same time, same place, for another talk at the online seminar series. So thank you to all of you.
Okay, thank you. Thank you all for attending this seminar. Thanks.
Yeah. So yeah, you see, we always have very good.
Yes.
Yeah.
Thank you.